Well, good evening, everybody, and welcome to the March lecture meeting for the Royal Astronomical Society of Canada, Toronto Centre. I'm the president, Ralph Chu, and it's nice to see everybody here tonight. So, before we get started, is there anybody here for the first time tonight? Our speaker for sure. Okay. All right. Well, again, a reminder to the newer members that the lecture meetings are one half of the recipe for our regular meetings here at the Science Centre. In 2 weeks' time, we'll have what we call our recreational astronomy nights, where we'll have some less formal presentations by our individual members. And we'll be talking about what we can expect for that meeting at the conclusion of the evening. To get things started, I'm going to call on Paul Delaney, our second vice president, to introduce our speaker. Paul?
Thank you very much, Ralph. 2 weeks from now, of course, that will also be the equinox. Spring arriving. So anyway, yeah, don't all leave just yet. It is my great pleasure tonight to introduce our speaker, and you can of the universe, gravitational waves, really hot topic of late, shall we say. Gravitational waves have been in the news for the last couple of years, and we're going to hear all about them tonight. Our speaker is Catherine Woodford. She heralds from the Far East, well, perhaps not the Far East, but Newfoundland at any rate. She completed her Bachelor of Science there at Memorial University in 2015. Shortly thereafter, headed for the University of Toronto, that's the other university in the city, and has been there with two supervisors, in fact, at this point in time, Norman Murray as well as Harold Pfeiffer. So we'll talk about that over a drink afterwards. At any rate, her work is obviously in theoretical areas associated with gravitational waves, and we'll hear, I'm sure, more about that. I also learned a great deal about Rotary and Rotaract tonight. She is a very active member of the community, and of course, as you can see by her standing here, she's also very interested in public outreach in astronomy. At any rate, without any further ado, Catherine.
All right, thank you. All right, thank you, everybody. Can everyone hear me? Are we good? No one's wondering what I'm saying or anything like that? Not yet. All right. Well, thank you so much for having me. It's always a pleasure to come talk to various aspects of the public, especially the RASC. I've spoken to the York Club as well, and you guys always have really, really great questions, so I'm really, really excited to get started. As Paul mentioned, we're going to be talking tonight about gravitational waves and how they're the sirens of the universe. So you might have heard before about various objects in the universe that are considered, the beacons, the candles, especially supernova. The supernova have been regarded as candles of the universe for a long time. We use them as standard candles. And over the last couple of years, gravitational waves have become our sirens of the universe. They are our standards in sound, if you will. So without any further ado, I'm going to get started. So the first thing we're looking at here is kind of our Canadian Institute of Theoretical Astrophysics and the University of Toronto connection. So what this is showing is the space-time around a binary black hole. And if you aren't familiar with what a black hole is, or let alone what a binary black hole is, don't worry about it. We're going to get to it in just a second. What we're seeing on the bottom here is the waveform of that space-time as it deforms. So this is an image made by the Simulating Extreme Space-Times collaboration, a collaboration that I'm a part of, as well as is associated with the University of Toronto. So what's happening here? We have our binary black hole that's in spiraling, getting closer and closer together. The space-time is getting more and more extreme. You can see by the red, the yellow, and the green. We've slowed down the video yet again because this kind of stuff happens on really, really short time scales. They finally merge. And we end up with our final black hole. So this is what we actually simulate. This is what we see in LIGO, or what we hope to see in LIGO, which, again, I'll get to if you don't know a whole lot about it. So I just wanted to give you a taste of what we actually do in CETA, what my work is on, what we actually look at on the day-to-day. As you can see, we have a lot of partners. So let's rewind that a bit. I talked about space-time. I said the word waveform. I said LIGO. I said SXS. Let's take a moment and kind of like unpack what all of that stuff is. So the first thing I want to kind of deconstruct is what's space-time? And then we'll lead into what's a gravitational wave. So we're going to start with space-time and gravity. So let's think about space-time. Here I have an image of our sun and Earth. Not quite the scale, but pretty close. And they're sitting on what we're going to consider as space-time. So this is a two-dimensional representation. A lot of the time what you can think of as a rubber sheet. So if you think about it like a rubber sheet, we have the sun, very, very heavy, very massive, and it's going to bend that rubber sheet a whole lot. And Earth is going to bend it maybe a little bit, but it's actually going to fall towards the sun in that rubber sheet, around that well, and orbit around it. So the idea here is that space-time in a two-dimensional analogy will bend and deform around matter, causing other matter to move. So the way that Einstein kind of encapsulated that was that space-time tells matter how to move, and matter tells space-time how to bend. You can also think of this in terms of how dense something is. So we're familiar with like lead, right? Lead is super dense. It's very, you can hold a small amount of it, and it's very, very heavy. Now think of a lead ball, maybe this large, it's going to be pretty heavy, versus a styrofoam ball of the same weight. So that styrofoam ball, several pounds maybe, it's going to be huge. It might be the diameter from this wall to this wall to have a couple of pounds of styrofoam. If I put them on a rubber sheet, which one will have a larger depression in that rubber sheet? My styrofoam ball that's really, really big, or my lead ball that's really, really tiny? Any guesses? Same depth. Yeah, they will be the same depth because they're the same weight. Which one might be more sharp? The lead, yeah, because it has a smaller area, so it's going to dip down the same distance, but it's going to be really sharp. So that kind of gives us an idea, thinking of our analogy here, of what happens to space-time when something really dense sits in it. So let's extend that a bit. So when I'm talking about something dense, I'm talking about a lot more dense than lead. So we're thinking about stars here. So the sun is actually quite dense in and of itself. It's a raging ball of fire in the sky, made of gas, much more dense than any of our planets. Well, let's take that a little bit further. So we have stars, and they're pretty dense. But then they go supernova, and they collapse. And what's left over is usually some of the densest objects we see in the universe. And sometimes we can't even see them. So stars mature, they go through their life cycle, they supernova, they collapse, and they can form a couple of different things. They can form white dwarfs, they can form neutron stars, and they can form black holes. And this is all depending on how large that star might be to begin with. So let's focus on the two extreme examples of that. Neutron stars and black holes. Really, really dense objects. Neutron stars are literally like nuclei, the center of an atom, held together by some of the strongest forces that we know of. And black holes are considered vacuums in space-time. They've collapsed. They're no longer really matter. So this is how compact and how dense these things can be. So in this example, these are two really, really dense stars, maybe neutron stars, maybe white dwarfs, something really compact. When these really dense things move on the fabric that is space-time, they cause ripples. And we can kind of imagine this on a rubber sheet with our lead ball analogy as well. If I was to roll that lead ball on the rubber sheet in a circle, it would start causing ripples out. If I started rolling it really, really quickly, those ripples would become more pronounced. So in this example, this is a better example. With our compact stars, they move around each other, they orbit around each other in space-time, and they cause a rippling effect in space-time due to their extreme density. And these waves, these ripples in space-time, is what gravitational waves are. So what does that mean? So really, we have a good idea of space-time. It's this sheet that everything kind of sits on. And we can distort space-time by having something really, really dense move around in it. But realistically, space-time can be rippled or manipulated by just matter moving on it. So if you have matter sitting in one spot, it doesn't really do anything. Once it starts moving, like me moving, it causes ripples. And we can actually create gravitational waves right here by making ripples in space-time. So I want everyone to put out their arms. Make sure you're not going to hit anybody, please. We're going to be fairly careful. So you're going to put out your arms so you're not going to touch anybody, okay? Now we're going to wave our arms back and forth really, really fast. We're waving, we're making gravitational waves, we're going, matter in space-time, we're doing it, stop. Okay, we just created a bunch of gravitational waves. But your arms are not all that dense, and nor are they all that massive. But matter moving in space-time creates gravitational waves. It creates that ripple. And that's what we're looking for. That's what a gravitational wave is. But as I said here, taking the extreme, the most dense, quickly moving objects we know of in the universe, like neutron stars and black holes, those gravitational waves are a lot larger and a lot bigger. But we can't actually see space-time. So what does a gravitational wave actually look like? What are those ripples actually doing? So this is showing the waves, these green motions. That's the gravitational wave passing through Earth. Note that it says scale of effect vastly exaggerated. If that really happened, we'd all be dead. The Earth wouldn't exist anymore. So vastly exaggerated, please. So these green lines are the gravitational wave passing through Earth. So in our sheet analogy, and that's exactly what it is, it's an analogy, we have ripples moving out. But space-time is four-dimensional, including time, right? Our three dimensions, length, width, height, length, and width, and then time on top of that. So when we think about that in our spatial dimensions, we have to think, okay, well, that ripple in space-time, those changes in space-time are actually changes in time and space. And I know I'm kind of saying the same words over and over again, but I'm trying to beat home a concept that is kind of really difficult, is that the distances are changing. The units of measure are changing when gravitational waves are passing through, when we have ripples in space-time. And that's what this is showing here. The distances, the shape of the Earth is changing as gravitational waves pass through. Again, not that extremely, but it is happening. So how do we measure this? How can we observe how the units of measure are changing? The units of distance in particular are changing. How can we see that? Or how can we measure that? And that's where LIGO comes in. So this is the second piece that I mentioned at the beginning. LIGO. LIGO, Laser Interferometer Gravitational Wave Observatory. It is based in the United States, with one detector at Hanford, Washington, and the other one in Livingston, Louisiana. And these bottom photos are just showing aerial views of the detectors. So what these detectors are, you might notice that they go in two directions. They have two arms. Each arm is about 4 kilometers long. And the idea is that gravitational waves, when they pass through, they will only change things in kind of one direction. So we should see things in one direction and not so much in the other, which is why we have two arms. We need a standard and a changing. And we need at least two, because what happens if that gravitational wave is moving on a diagonal? We'd see it in both, and we wouldn't be able to tell very much of anything. So a little bit of background on LIGO. It's actually been around for a few decades. And the ideas behind LIGO have been around for longer than a century. People have literally started and ended their careers in LIGO, and unfortunately some of them before gravitational waves were discovered. A little depressing. The actual machines were starting to be built in 1994 to 2002. It took a long time to build these guys. And then the first observing run was from 2002 to 2010. We didn't see anything. Again, a little depressing. one of the reasons why we didn't see anything is that even though these arms are so big, they're 4 kilometers long, there's a lot of noise in the data. And it was really hard to understand, okay, well, what is the noise coming from? How do we get it out of there? How do we make the detectors so that they don't have noise? How do we avoid it? And we'll talk about what noise comes from in a second when we actually look at what's inside these guys. What's important here is that we do have at least the 2 detectors. But there is one more. And you might have heard of them. A detector called Virgo. Now this one isn't an abbreviation for anything or anything like that. Virgo is actually named after the Virgo cluster of stars. So there's not anything but there. And this guy is sitting in Italy, actually relatively close to the Leaning Tower of Pisa. And it's agreed to work with LIGO. So now it's not just the LIGO collaboration, it's the LIGO-Virgo collaboration, which is pretty great. So as I mentioned, we kind of needed at least 2 detectors to figure out where a gravitational wave was coming from or if we were seeing it. And you can think of it the same way of why we have 2 ears. If we had 1 ear, same thing for people who are deaf in 1 ear, you can't really figure out where a sound is coming from unless it's directly on one side. We have 2 so that you can pinpoint where a sound is coming from. Same reason kind of why we have 2 eyes. We can negotiate depth. But can you imagine if we had 3 ears? Like one right here? That'd be great. We could pinpoint sound so accurately because we'd have 3 points of data. So that's the argument with having more and more detectors, is that 2 is pretty good. You can find things relatively well. But 3, that's fabulous. You can find things so much better. But again, noise is a pretty big issue. So why is noise an issue? Where is that noise coming from? Well, to do that, we're going to need to actually look at what's inside these arms and what the detector is doing. So the first thing we want to think about is what does an interferometer do? What does interferometry mean? In interferometry, essentially what it means is that you're using electromagnetic waves, in this case a laser, and you're extracting information from the interference pattern of that laser. So we're going to do a little bit of a science lesson here. Electromagnetic radiation is essentially light. And light can behave as a particle or a wave. So in its wave capacity, it needs to have a wavelength or a waveform. Keep stepping on it. And the idea here with waves is that they can be constructive and make bigger signals, or they can be destructive and create weaker signals. So with an interferometer like this, they specifically built it so that the arms are exactly the same length. So when the laser goes up each arm and it comes back, it destructively interferes completely, meaning that there is no residual information. That's where you see it comes up and it comes back and there's nothing left. So when we see a signal, we should hopefully see something in the detector. In this case, instead of destructively interfering, when we have our gravitational wave passing through and one side gets longer, the other side gets shorter, and vice versa, it now constructively interferes sometimes as the wave passes through, giving us a signal. Unfortunately, more than just gravitational waves can cause the laser to give us a signal. Things like trucks driving will shake the mirrors, causing the wavelengths to kind of jitter a little bit and give a constructive interference. It can also be for people stomping too loudly on the upper floor. It can be from cities nearby. It can be from earthquake rumbles in the ground around the detector. And most famously from the Louisiana detector, it can also be from local residents shooting at alligators with their shotguns. I kid you not, that was an actual source of noise. They had to put up a fence around the detector and say, like, okay, there are no alligators in this area. We don't have to worry about shotguns being a source of noise anymore. So all of these things can cause the mirrors, which are reflecting the laser, to move back and forth a little bit, which then throws the whole experiment into jeopardy. And these really, really tiny sources of noise are a really big problem for gravitational waves. Remember how I said matter moving through space-time is what causes gravitational waves, and we waved our hands back and forth, and that created some? I did say that it was very, very small, the ones that we created, and that the ones from dense stars or black holes would be a heck of a lot bigger. But not quite as big as like what we saw with the Earth, right? That was not quite that big. So how big is it exactly? How large are gravitational waves from orbiting black holes, the most extreme system that we really know of in the universe? Does anyone have any guesses? Like in terms of how much the distance actually moves. Is it a meter? Definitely not. We'd be dead. A micrometer? Maybe, yeah. Micrometer is 10 to the negative 6 meters. Any other guesses for how much that distance might change? Millimeters, 10 to the negative 3. So keep in mind that light has like a really big wave spectrum. It can be as long as radio waves, which is like a kilometer long, or they can be as small as like gamma rays, which are like nanometers. So it depends on what you mean by a fraction of a wavelength. Yeah, so for these ones, they're in like the micrometer range. So maybe like a fraction of a micrometer. Nanometers 10 to the negative 9. Okay, so why don't we actually look at how small a gravitational wave is and what LIGO is actually trying to see? Why these sources of noise are such a big deal. This is a proton, okay? A singular, or sorry, not a proton, a hydrogen atom. A singular proton and a singular electron, imaged here by an electron cloud. So now we're going to actually look at how much the distance changes in the LIGO arms, what we would expect to see over a 4-kilometer arm. Oh, nope. We want to see the other video, this one. So this is our hydrogen atom. So each grid point is 10 smaller, into the proton, 10 smaller, 10 smaller, 10 smaller, 10 smaller. That's our proton, 10 smaller. We're keep going here, 10 smaller. And this is how much we expect the arms to change. That is 1/1000th the diameter of a proton. Okay? That's 10 to the negative 18 meters. That's how much we expect those arms to change. So now you might understand why someone like stomping on the upper floors of LIGO might be a problem. Or someone shooting their shotgun at an alligator. I mean, for most experiments, that would be like garbage. We wouldn't even see that. But for this one, every bit counts. So this is actually why we need to do a lot of simulations. This is kind of what I showed you at the beginning, right? So to extract gravitational wave information out of LIGO, where there's so much noise and there's so much stuff that can go wrong and we maybe can't see it all that well, we need to know what we're looking for. And that's where numerical relativity comes into play, which is what we see here. So this line, this upper line here where it says strain, that's what we should see in the detector. All strain is the amount that the distance changes, delta if you will, over the total distance. So that would be our 10 to the negative 15 meters over the 4 kilometers. That's what strain is. So we need to have a really good idea of what we're looking for in order to be able to pick it out of the data, in order to be able to see what it is. And to do that, we have to do something called matching, where we need a lot of these templates, a lot of these waveforms to compare to the data and say, is this a detection or is it not? What size are the black holes? Are they spinning? What else can we tell about the system? So this is what a simulation looks like when we can control the parameters. And these are what the templates look like that LIGO has. All 677,000 of them. But what does the real deal look like? What does real LIGO data look like? We've talked about how small it is. We've talked about sources of error. And now I'm telling you this is what we use to kind of see if we can find something in the data. But what does the actual data look like? like that. Does that look familiar? The shape compared to that? Do we see a similarity, especially at the end there near 0, times 0? You see it? This is actual LIGO data from September 14th of 2015. The orange represents the data we have from the Hanford detector in Washington, and the blue is from Livingston, Louisiana, overlaid so the time matches up. And you can see pretty clearly here the similarities between this data and the waveform I just showed you that we actually create with numerical relativity. This was the very first gravitational wave ever discovered, GW 150914. This was a pretty big deal. It might not look like much, especially considering it was, 1/1000th the diameter of a proton. But what did this signify? What does finding gravitational waves 100 years after Einstein forecasted them mean? A, it was a test for general relativity. We are always testing our theories. Things don't become laws overnight, and they don't become laws very easily. We have to test every single situation over and over and over and over again. So by finding gravitational waves, and by saying, yes, they exist, and we found it, it was a big boost for GR. We said, yes, that this theory is correct, including this particular situation. It was the very first observation of a binary black hole. So we had seen some black holes before. Seen is the operative term because you can't actually see them. You can detect stuff around them, which indicates that there might be a black hole there. But this was the first observation of a binary black hole. 2 black holes orbiting around each other. Had never seen anything like that before. Thought that they should exist, but had never had any data about it. It was the first evidence of stellar mass black holes. Up until this point, we knew that there were supermassive black holes in the middle of galaxies, and we knew that there probably should be stellar mass black holes, but didn't have any evidence for it. So what a stellar mass black hole means is that it's a black hole that's approximately the same mass as the sun, less than 20 solar masses, 20 times the mass of the sun. We thought that they should be we've seen ones that are much, much larger, much more massive, but we hadn't seen any of this size. It was the smallest detection attempted by science. Not just in astronomy, but by science, period. Not this includes nanomaterials, this includes medicine, this includes everything. It was the smallest detection ever made. And it was done by astronomers, It was pretty great. And on top of everything else, it was the most energetic event ever observed. What does that mean? It means it was more energetic than any supernova. It was more energetic than any active galactic nuclei. It was more energetic than any neutron star or magnetar or anything. It was more energetic. More energy was expelled during this one event than all of the starlight in the observable universe combined. That's a lot of power. About, 3.6 times 10 to the 49 watts. So a lot of stuff in that one little observation. And when we say sirens of the universe, remember, the gravitational waves are what we consider the sirens of the universe. That's because the frequency that these waves come in at is actually very similar to what sound waves are. And we can transpose them into audio. So maybe we want to hear some gravitational waves. Who wants to hear some gravitational waves? Yes, of course. Who wouldn't? So 100 years of analytics, 50 plus years of engineering, 20 years of painstakingly trying to get the NSF to give you money, 10 years of observation that failed, the smallest detection ever made, the most energetic event ever observed, and it sounds like a chirp. Cool. And this is actually what we characterize this now. So this little banana shape, we call it a chirp because of the sound. So now when we look at data from LIGO, we look for that characteristic chirp. It all comes around. So GW 150914 was the first one we found. But I'm sure as you guys have heard, there's been more. And LIGO's continue to churn out more stuff. So these are the binary black holes that we found so far. So all of the names here are reflective of the dates. We have some in 2015, some in 2017. This guy right here is LVT. He's not a gravitational wave because the signal-noise ratio wasn't good enough. He's a little bit weak. And on the side here, we have solar masses, so how large they are. So 150914 was like the biggest binary black hole we had seen. And then we had seen a couple cents, all in the stellar mass black hole range, which is great. And for the work done by LIGO, 3 individuals were awarded the Nobel Prize in Physics in 2017, including Kip Thorne, Rainer Weiss, and Barry Barish, quote unquote, for decisive contributions to the LIGO detector and the observation of gravitational waves. Now, these 3 individuals are not only instrumental for LIGO, they were instrumental for gravitational wave theory, for numerical relativity, and everything that falls under those umbrellas. Remember at the beginning I mentioned the SXS collaboration, the Simulating Extreme Spacetimes collaboration, which is responsible for a large portion of the LIGO catalog, of the templates they use. Kip Thorne was a founding member. So he's not just responsible for the LIGO contributions, he's responsible for the numerical relativity contributions, as well as Rainer Weiss and Barry Barish. So these are really big contributions here. But it doesn't stop there. So these are the binary black holes we had found up until August 14th of 2017, a couple of months ago. There's one more detection I'm not including on here. Do you see it? Did everyone see where that was? This is before, this is after? Yeah? All right, so GW 170817. This tiny, tiny little guy all the way down there. Do you guys think that's a black hole? All the way down there in that like 0 to 10 range? Is that a black hole? Is that a binary black hole down there? It's not. Blew it out of the water. So this is no longer a map of binary black holes discovered by LIGO, but of gravitational wave objects. Yes, that's right, folks. LIGO did not just discover binary black holes, they found binary neutron stars. And so how do we know that wasn't a black hole? So the first giveaway was the masses. It's small, real small. But there's a couple of other things that told us that this wasn't 2 black holes that merged and they just happened to be tiny. And one of the major ones was the signal. So on the y-axis here, it's the signals, and on the x-axis is time. So some of the major ones, see they're pretty short. This is time in seconds. GW 170817 is in orange on the bottom, and it is going. It's still going. We're at 20 seconds, and it keeps going. Now, the length of the signal is a telltale sign that this was not a binary black hole, because binary black holes, when they start getting close to their merger, they just go for it. Binary neutron stars can be a lot more stable, and there's a lot of other stuff happening. One of the major things is that with neutron stars is that we can see them with electromagnetic light. We can see them in the optical, we can see them in gamma rays and X-rays. And so not only was the length of the signal, it's still going, by the way, not only was the length of the signal a telltale sign that this wasn't a binary black hole, oh, there it goes, just after 55 seconds. It was also the EM counterpart, the electromagnetism counterpart. So the first one, the length of the signal, huge. But the bigger part of this was what else we saw. So LIGO saw the gravitational waves first. And Fermi, a gamma ray detector, also saw something. Very, very close afterwards. And not only did they see something, but we saw it in X-ray, UV, optical, infrared, and radio. Every kind of electromagnetic light that we know how to observe, we saw this event in, which was amazing. So the first thing I also want to mention is that this is actually a figure from the detection paper. And this detection paper was 59 pages. And pages 36 to 59 are the author list, just so you know. Because all of these different detections were all different telescopes, collaborations. People had to work on this. So this officially went beyond LIGO. And you can certainly find the paper. This is just the first page of it. Multi-messenger observations of a binary neutron star merger. Open access, you can look at it. What I would like to point out here is that we do have some University of Toronto people scattered in there, or circled in red, and then from Dunlap in blue. I did actually look through and try and find all my colleagues, and I think this is everybody. Yeah, so there's a lot of people. So what does a collaboration that big look like? How many people, how many observatories, how many collaborations were on this paper? It was 4,000 authors, 900 institutions, and 70 observatories all over the globe and in space. So it was LIGO Hanford, LIGO Livingston, and Virgo, and then all of the blue dots you see were the individuals and collaborations and institutions that did the electromagnetic follow-up, the counterpart. What really told us everything we really needed to know about this detection, including one in Antarctica. So this was global. So not only was this an amazing scientific discovery, this was also an incredible feat for the scientific community to come together and work together to do this publication. There was no scooping, there was no backstabbing, as far as I'm aware. It was just about the science. So what did we learn from all that? All of these individuals that came together to tell us the story of a binary neutron star, the very first detection of one. One of the really cool things about it, so that on the left-hand side here I have a brief simulation photo of what they believe the merger might have looked like of the binary neutron star, all this matter around it. One thing that was really big in the media was that it was like, oh, this is where gold comes from, and platinum. What does that mean? So it wasn't just, gold and platinum that comes from a binary neutron star merger. It's all of these guys. So elements in general, a lot of them come from the Big Bang, right? And then some of them come from stellar evolution. Stars burn and they create new elements. But then almost the entire second half of the periodic table had a big question mark on where it came from. And we maybe knew where some of them came from. We had some reasoning, or we knew where a small amount may have originated. But a lot of these, we either didn't know where it came from, period, or we didn't know where most of it came from. And the information we got from not only from the LIGO-Virgo collaboration, but also from the electromagnetic follow-ups, told us this is where a lot of our elements come from binary neutron star mergers. Because a binary neutron star merger kind of leads to something called the Killa Nova. So we know of something called a supernova, the explosion of a star. A Killa Nova is kind of like the big granddaddy above that. A lot of energy, a very violent explosion. That the energy levels coming out of this Killa Nova is what can create most of the heavy elements. And that was one of the big things that came out of this observation. It also confirmed that a Killa Nova, because it was the first significant observation of a Killa Nova, it was a confirmation that it was also a gamma ray burst, because we saw it in gamma ray from Fermi. Didn't know that either. So a lot of these random gamma ray bursts that Fermi was picking up maybe now have sources. That's pretty incredible. As I mentioned, it's the confirmed source of the heavy elements, so most of them heavier than zirconium. The first observation of the merger of a neutron-star binary, same way that was the first observation of a binary black hole. And one of the really big things that people don't necessarily focus a lot on, because it's very, very far into theoretical astrophysics, is constraints on what a neutron star actually is. So as I said, we know that a neutron star is kind of just like nucleonic material. So protons and neutrons just kind of like forced in together in a big star. But it has layers. It has a core. What does it look like? How do things manage in there? Is it plasma? Is it magic? Unicorns? We don't really know. So neutron star modeling is a really big part of theoretical astrophysics. And there's a lot of theories about it. And we can't really test it because you can't make a neutron star in the lab. So this observation of a merging binary neutron star gave us a glimpse at the interiors of these guys, of how much energy gets released. And that restricted what neutron stars can be. Admittedly, it was just one observation. So we couldn't restrict a whole lot. But the point is, we found something. And we started somewhere. And that's a big step forward for not just gravitational wave observing and astrophysics. It's a big step forward for astrophysics in general, theoretical and observational. And lastly, it gave us a bound on the speed of gravitational waves. Right now, we believe that gravitational waves should travel at the speed of light. That's what Albert Einstein forecasted. And by observing not only gravitational waves, but light and various kinds of light from the binary neutron star merger, we were able to put that bound a little bit closer to light itself. So we're getting closer and closer to validating GR as a theory overall. And the very last one, biggest one here, is it's the beginning of multi-messenger astronomy. As I said, this was a huge collaboration. 4,000 authors, 900 institutions, 70 observatories. And everyone worked together on this. This was a massive discovery. But one of the bigger parts of this as well is that it was the birth of multi-messenger astronomy, of the scientific community in observational astronomy coming together and working together to make discoveries that can change how we view the universe. So we're not just seeing it, but we're also listening to it, and we're doing both at the same time to give us as much information as possible. So I'm going to leave you with this simulation of what we believe the binary neutron star merger to look like. And I want you to remember that it took about 100 years to discover gravitational waves. And a lot of people devoted their lives and their careers to it. And it would not be possible without those individuals committing to observing and finding the impossible. Or rather, willing to listen to the sirens of the universe. Thank you.
Okay. Out the very edges of science, I have a few questions. You can certainly engage. I'm going to hand my microphone over to Alan, who's going to run around like a rabbit to make sure that you can all hear the question.
Fabulous.
Do you know why the detectors were placed where they were in North America rather than putting them in places that are more isolated, where maybe wouldn't have as many small earthquakes or people shooting alligators?
First off, it's the States. Where are you not going to have people shooting shotguns? Anyway. Second of all, it has to do with the land available. So a lot of the land in pretty much any country is owned by someone, right? It's not necessarily all government owned. And a lot of it that is government owned, you can't just give to the NSF, or the National Science Foundation, for those of you who don't know. So where they were placed was just where the NSF was able to give to the LIGO collaboration. It wasn't necessarily, oh, this is the optimal spot so we can put it here. Because realistically, the optimal spot is in space. And for those of you who follow it, ELISA, which is our space detector that we are currently like manufacturing and putting together and testing, should go up in 2025. Cries, it was supposed to go up in 2018. So it's not so much like this was the optimal point as so this was where was available at the time. Because again, as I mentioned, LIGO was considered a failed experiment for about 20 plus years. Unfortunately, yeah. Good question. I'm pointing, but I know you need a microphone, sorry.
How long after LIGO saw the neutron stars before everybody else sort of everything sort of went away?
So that's a good question. So this is a bit of a difficult question. So LIGO saw it, and there was a bit of struggle there because it was right on top of a glitch. So one of the detectors didn't actually see it, which was an issue, and we had to whiten that data a lot. I say we, I'm not even in LIGO, but my collaborators had to whiten a lot. And so it actually took them something like 45 minutes to get it throughout the whole collaboration to say, like, there is something here, and it's not a binary black hole. So then after that, they were able to reach out, and Fermi said, okay, well, we saw something 1.7 seconds later, and it was in the same part of the sky. So once that was confirmed, then it was a reach to all of the telescopes that they had that they could possibly contact and say, you want to look at this quadrant right now. And those who could did, but keep in mind, gravitational waves you can observe 24/7, as long as the detectors are up. But electromagnetic light, especially in optical and a lot of the bands, you actually need to wait until dark, and or for the Earth to rotate so that you can look at that part of the sky. So the detectors that they wanted to look at it were in Africa, which was 8 hours away from being able to see it. So the communication was out, I believe, within like a 2-hour span. Because LIGO, how it works, people get put on rotations, and you have like an alarm on your phone that'll go off if the detector sees something, and you immediately have to get up. It doesn't matter if you're asleep, if you're at a wedding, if you're at a person's funeral, it doesn't matter. You gotta get up, you gotta get to a laptop and an internet connection and run the data. And they can do that really, really quickly. And then it was a matter of hours, very, very close time span to get the word out. But then because EM is a little bit more finicky, and depends on like the orientation of the Earth and whether it's day or night, that took a little bit more time. But they were able to see stuff. So it was within about 8 hours that we had significant data, and then they saw stuff from the longer wavelengths later on, like in days, because it takes longer to arrive. Yeah, so like in terms of the actual time frame when everyone knew, it was relatively short, but then there are restrictions with observational astronomy that you can't just point a telescope through the Earth and see something.
Black holes, the neutron.
Oh, so okay, so they saw very, very close to the merger of the neutron star. When I showed you the signal, they didn't pick up the signal at the beginning. They picked up the signal at the end, and then they retrospectively looked through the rest of the data. Because the in spiral, what we call like when it's getting close to merger, that isn't always strong enough to just pick up. Sometimes it will detect it, but oftentimes it won't. You'll see it you'll see closer to merger than you retrospectively match. So it was actually at the merger when they saw it, and Fermi just happened to be pointing in that direction, and they saw something. Yeah. So it was kind of a coincidence, but also a good coincidence. So that was pretty great. Oh.
How do you determine the direction that the event is happening from those 290-degree angles?
That is an excellent question, and I have a slide for that. Oh, okay, Here we go. So this is a localization map. So in particular, GW 170814, that was a binary black hole that was found with both the LIGO detectors and Virgo. And 170817, that yellow one there, was the binary neutron star that they found with not just the gravitational wave detectors, but also with the EM detectors. So how you find it, as I mentioned before with like a triangulation, you use your ears to focus on where a sound is coming from. The more detectors you have, the better you're able to focus. The same thing with GPS. One satellite, you don't get a very good GPS signal. 2, you have 2 localized, it gets better. 3, even better. 6, amazing. And it gets better the more satellites you have. Same kind of idea. So it's using a triangulation method. So with the waves coming in, we can say, okay, well, the detector has some blind spots, so it can't be in there. And we know that it has to be in this region. And then you look at the data from the other detector, and it's like, okay, well, it has to be in this region. And then the overlap is where it must be. So then you get more and more accurate with the more localizations you have. And especially with Fermi and the EM detectors, those are fairly small because we've had electromagnetic detectors for a much longer period of time, just in terms of like centuries. So you overlap all of those localization maps, and it gives you a point on where it should be. So that's how it's done. Good question. Not many people want to know about how the localization happens. Yep.
Okay, so I'm a little surprised that it's possible to pinpoint the location that well, because I'm thinking of a very basic model. If I'm standing in a pond, I'm throwing a stone in there, the paddle moves away from me and towards me, and then somebody's over there throws a stone in there, and you get a pretty messy set of waves, I guess.
So what you're, yeah, sorry, go on.
Well, I was just wondering how you can decipher from all these various incoming and crossing waves to say it came from there.
Right, so your question is not so much localization as it is how can we pick apart different signals and what happens if they overlap and there's a bunch of stuff happening at the same time. So there's a couple of different kinds of gravitational wave signals. One of them being something called stochastic, which means they're just kind of like underlying gravitational wave signals. We expect there to be gravitational wave signals from the Big Bang, for example. However, those gravitational waves are so, I don't want to say small, but they're so out of the range of LIGO that we can't see them. So another thing that's important is that LIGO has a limited range of what it can see. We know that there are not only stellar mass black hole binaries, but that there should be supermassive black hole binaries, like galaxies orbiting around each other. But the range, the frequency range at which those guys are orbiting is just really outside of what LIGO can see. So first off, there's a limited number of systems or kinds of systems that LIGO can even detect, just because of its sensitivity range. Second of all, these events aren't happening in a really high frequency. So they do have a frequency range. Rates of occurrence. So right now, for binary black holes, we expect between 2 and 600 per cube gigaparsec per year. And what that means is that we can actually only see binary black holes out to a certain distance right now. Because as the waves get further and further away, the event gets further and further away, those waves get dissipated, they get weaker, so we can't see them anymore. And for binary black holes, we don't actually expect that many a year. So even if there's 600 a year within a cube gigaparsec, that's like 1 or 2 a day. And the chances of them being overlapped are pretty small. And then for binary neutron stars, it's a similar wide range because we just haven't seen very many of them. So the reason here is like, A, we only see a certain kind of system with the LIGO detectors right now. It has a limited sensitivity. And the other one is that we don't expect these guys to be happening at a high enough frequency that we actually need to worry about them overlapping. It could be something we need to worry about when we have really sensitive detectors or multiple detectors at different frequencies, at different sensitivities. Right now, it's not a concern. But that's a very good point.
I think you said that one of the results of the neutron star merger is that you gained insight into what's actually taking place inside.
Mm-hmm.
Does the merger of black holes offer that same hope?
So if we could see them, maybe. So one of the big differences between neutron stars and black holes is that for neutron stars, you can actually see them in electromagnetic light. Not necessarily the optical, but you can see them from telescope detections, regular observation detections. Whereas with black holes, that's kind of what makes them so difficult and tricky, is that they don't emit light, period. So the only real way to even detect them is with gravitational waves. So we wouldn't be able to use the same methods, at least, to do that, because we can't see an electromagnetic counterpart from these detections. And if we, well, there is no if, we can't. So unfortunately, not so much. Unless we can start pulling more information out of the gravitational waves themselves, I don't forecast that being possible until we get our theories up to speed. Yeah, but really good point, really good question. The string theorists would be all over that. Absolutely.
How much better will the space-borne detector do than the Earth-borne detector?
So much. So remember when I said about the gravitational waves, what we actually detect is something called a strain. And the strain, as I described, was the change in distance over your distance. So for the 4 kilometers, that would be our 1/1000th of a proton diameter over the 4 kilometers. And you can reason that as long as that strain number is going to stay the same no matter what. So that means our actual displacement that we see in longer arms can be bigger, which means the longer the arm we have, the better our ability to detect, or the better our sensitivity, or the wider range of detectors we can have. So the LIGO arms are 4 kilometers long. The Virgo arms are 3 kilometers long. And that's about as good as we can get on Earth. So good, in fact, that we actually have to start accounting for curvature of the Earth in the LIGO detectors. It's pretty. I didn't think that was a real thing, but it is. In terms of actually needing corrected 4 kilometers. Anyway, the ELISA arms we hope them to be 1 million kilometers long each. So that's a factor. That's like 2 factors. That's 2 orders of magnitude bigger than what we have right now. So what kinds of systems we expect to see with that? Hopefully a lot more binary black holes and binary neutron stars, maybe things that, maybe some stochastic stuff, because hopefully they'll be a lot more sensitive. But until we actually get the detector up there, it's kind of hard to say. But we do hope with the space ones, because there's more space out there, we can make the arms a lot bigger, and so our detections can be a lot better. They wanted that, but because of the budget cuts, it's 2, I believe, at this point. Maybe it'll go back up, but yeah. It's also been pushed like 7 years later, so it's hard to say what will happen at this point. But yes, having three arms would be a lot better than having 2.
That, the graph you showed of the first detection.
So like the raw data?
Yeah, well, just the overlap of the 2 detectors. Is it expected that they would be that close in amplitude? I mean, I would expect if the different orientations in different places on the Earth, that the amplitude of the 2 detectors would be different. Why would it, I mean, depending on where it came from, if it's oriented this way, it could be, I don't understand why it would be so similar. Is that always going to be like that?
So that's a good question. So this is a little bit misleading, because it's not like I'm showing you the strain per arm. Because you're absolutely right. Depending on orientation, different arms will have different strains because the gravitational wave is hitting them differently. It's a different orientation. So what this is showing you is the overall strain averaged over both of the arms. So unless the gravitational wave was hitting at a point that neither detector could see it, which is impossible given that the Earth is round. I'm not going to entertain any ideas of flat Earth, by the way. I'm not even going to start that. So because it is round and it's 3-dimensional, you will have to have a gravitational wave hitting at least one of them in a way that you can see them. You can see it. If this one had happened to be that it hit one detector and it was a blind spot for the other, then yeah, it would have been really hard to put that together. But for this one, it did hit both detectors so that you could see it. And when you take the information from both arms, if the gravitational wave is hitting in such a way that it's not a blind spot, so it's not hitting like directly perpendicular, yeah, then you would expect it to be the same strain. Absolutely. So there's really only kind of two options. Either you see the same or you see nothing. And if you see nothing, that means it's a blind spot and you can do a better job on sky localization because there's only so many places in the sky where it can come from that it does hit a blind spot for either detector. Yeah, so in terms of where they are on the Earth, that just gives you a better idea of sky localization, but it doesn't really play anything into the amplitude.
Are they like 30 degrees from each other, or does it matter?
Oh, shoot, I don't remember those numbers, unfortunately. But yeah, no, they're not perfectly aligned. It's not like one's like this and the other one's like this. It's like one is slightly this way and the other one's slightly like the other way. They are off by some degree, but I don't remember exactly what. I don't even think it was on purpose, actually. It's just like how the land that they were able to get was oriented and like how they could maximize the length of the arms. Well, I mean, they would have been different anyway just because of the curvature of the Earth. I mean, they're on opposite sides of the continent. So no matter what you did, they were going to be pointing in slightly different directions.
One thing I'm wondering is speed. I mean, we always talk about the speed of light. Is there any feel for the speed of a gravitational wave?
Yeah, so I mentioned this very, very briefly. In Einstein's theory of general relativity, the theory is that gravitational waves should travel at the speed of light. That's the idea. Excuse me. But of course, we need to make sure that that's the case, because if that's not the case, then GR isn't completely correct. We have to think about other things. So what each detection gives us is a new bound. And especially when we can compare gravitational waves to light itself, that gives us even stricter bounds. So the binary neutron star event is what really gave us a better restriction on it. And right now, the restriction on it, I believe, is something like 1 part in a billion difference from the speed of light itself. I mean, small enough that you could detect it, but fairly small that we're still really, really confident in GR. Don't quote me on that number. I'm trying to remember, but it is a very, very small part. It is very, very close to the speed of light. We know that for sure. Yeah, good question. Oh, this gentleman here needs a question.
Thank you. Good so far. Is the sensitivity of these devices improving still, or have they reached sort of the limit that they can get to? And
we are always improving, always. So as I flip through this, one thing you might note is that we don't have any detections as of late, like in the past couple of months. And that's because LIGO is still trying to reach its design sensitivity. So what I have here is the green line is LIGO as of 2010. The red and blue is LIGO for Livingston and Hanford as of 2015. And then the gray bottom line is the sensitivity that we hope to get, what its design sensitivity was for. So essentially what you should take away from this is that the lower this line is, the more detections we can see, or the better we can see them. That's the idea. You want it as low as possible, as close down to 0 as you possibly can see. So strain noise is going to be on your Y, and the frequency is on your X. So the lower strain that we can see, the more detections we can see, the better we can see them. That's the idea. So LIGO routinely shuts down, and they get new equipment, or they improve equipment, or they better the vacuum chamber, or what have you. So it's constantly in a state of upgrade. So just so you know, I showed you what the interferometer looks like, but it is 4 kilometers long. The mirrors actually need to be in vacuum. It's not just the fact that it's 4 kilometers long, you can shoot them in air. No, no, no. You have to vacuum a concrete tube that's 4 kilometers long on either side. So it's a lot of work, it's a lot of engineering that goes into this. The mirrors are something on the order of 10 kilos, I believe. They're pretty big, they're like this big, and they're just solid silica. And they're hung on some of the thinnest silicon wires that has ever been made, which is all very sensitive, and we have to try and continuously make them better and all this stuff. So it does go down for upgrades regularly. It's not at design sensitivity just yet. Hopefully, it will come back online later this year at design sensitivity where that gray line is, and it'll be able to detect more stuff. But always looking for improvements, because not only does like theory and stuff like that get better, technology gets better, and engineering gets better, which then will give us better detection equipment. So we're always pushing it.
We are on, sorry. Okay. Literally, the frontiers of astronomy continue to expand, and it's an exciting time. We thought, 20 years ago when we started finding exoplanets, that might be the next greatest frontier, and for a while it was. But now with LIGO really coming on stream, truly the sky is the limit. Thank you very much indeed, Catherine. Wrap it up and then go on to our announcement.
Okay, I guess we depleted the batteries in the other one. Okay, well, one thing I was going to say was that this was a very enjoyable lecture, and as a science communicator, wow, I really enjoyed just your ability to put the ideas across.
Oh, thank you.
So thank you so much for coming tonight to talk about gravitational waves, and this is just a little token of appreciation for you, and there's another token that will be coming in the mail. Because the treasurer isn't here tonight. But again, on behalf of everybody here and online, thank you so much for coming to talk about gravitational. The calendar is photographs done by members of the RSC across the country.
Oh, wow.
And so there's a picture of the month on every page.
Amazing. Wow, thank you so much.
Our pleasure. Thank you. Okay, so what we're going to do is to wind up by so we're going to finish off by just quickly going through the announcements again, as we usually do. And our next meeting in 2 weeks on the 21st is going to be our recreational astronomy night. And Michael Watson will be coming back to present the sky this month. Chris Vaughn making Le Monde, not lemonade, as I had originally thought. Tips, tricks, and targets for observing the full moon. And as far as I'm aware, we still have that one slot left for that evening that's still open. So again, if anybody has an idea for a presentation, please contact Paul Markov to let him know that you're interested in doing a presentation that night. The next lecture meeting is going to be on, how did I manage to, I did this slide at 1 o'clock in the morning, and I missed things. Yeah, I did a little bit of a time warp. Anyway, it is the 11th of April, not the 7th of March. And our guest that evening will be Jake Clues, who's with the Earth and Space Science and Engineering program at York University, talking about the search for water in the solar system. Okay, solar observing. Somehow we've managed to change the layout of the slides a little bit. But again, one of our regular observing sessions every month, this time on Saturday the 24th of March from 10 till noon on the telescape. And Sean is our usual host for that, and he'll be making the go, no-go call on the usual communication channels, either late Friday night or first thing on Saturday morning. Other observing that we will be going with, next Dark Sky Star Party is next week, first clear night of Monday through Thursday of next week. And I believe it is going to be at Long Sault. Yes, no, maybe? Who's running it this time around? I believe it's Long Sault. Okay. Yeah, I think the last meeting we had that discussion, and the decision was that it was going to be at Long Sault. So there we go. And the map is on the back cover of Scope. City Star partying the following week, which is the week of the next meeting. So it's the first clear night of Monday, Tuesday, or Thursday of that week at Bayview Village Park. Okay. For new members who are online, just an announcement that we have First Light starting up in 2 weeks' time. It's a 3-meeting series of talks which cover things about the center. It's an orientation program, so the presenters will be talking about programs and activities that we run. There is a talk on astronomy on a budget. Yeah, amateur astronomy, observing, black hole, synonymous, yes. So there we go, especially when you get into astroimaging, right? And so again, that'll be addressed, and also some advice about getting started with observing the sky. So those meetings will actually be running concurrently with the next 3 meetings on the 21st of March and then the 11th and 25th of April. So unfortunately, you have to choose either between First Light or our regular meetings. You can register through the link on our news page on the website. And we do need you to register online for that so that we know how many people are coming for the session. Okay, we are looking still for some help with Twitter and Facebook to give our current contributors a little bit of a break. And again, if you're interested in helping out with that, please talk to me or Tom Luton, or also Katrina, whose email is there on that slide. A reminder that the CAO, the Car Observatory up near Thornbury and Collingwood, is available for your use. And now we don't have quite as much snow and ice to get through to get to the site, merely mud and sundry things like that, and a 2-foot deep cut across the access road. So you're still going to have to park at the top of the hill and walk in, because the northern approach to the property is still inaccessible until the town regrades the road. So again, you can book online once you've signed into the website, and the form is right there for you to use. Also a reminder that we do have the loan program with all the instruments, and I see that we've got at least 2 of our managers there, George and Mark. So again, if you want some more information about what's available that you can pick up for at the next meeting, please talk to those gentlemen. Okay, and then finally, an invitation to join us and the speaker at the Granite Brew Pub after the meeting, for some light refreshments and chat. And that is everything. Is there anything else that anybody has in the way of announcements that good and welfare? Chris?
Just a public service announcement to remind everybody that Saturday, March 17th is the noon, and that's the prime weekend for a Messier Marathon, if anybody's interested in attempting that.
And also the clocks go ahead this weekend, so.
Yes, daylight savings time on Saturday night. Sunday morning. That's right. So we can all get screwed up on our time clocks. Right.
You lose an hour of observing. Oh, well, what do you do?
Yeah. It'll be raining, don't worry. Okay. Anything else? Okay, well again, thank you very much for coming out tonight, and we'll see everybody in 2 weeks' time. Good night.